Limit properties. Our objective in this lesson is to use properties of limits and an analytical approach to find the limit of a sum, a difference, a product, a power, a root, a polynomial, a quotient, an average rate of change, and a difference quotient. Previously, to evaluate limits, we used graphical and numerical approaches. Now we will look at analytical approaches. Let the limit as x approaches c of f of x equal L and the limit as x approaches c of g of x equal k. C and b are real numbers. N is a positive number. Then the following will be true. This is used a lot. The limit of a constant. The limit as x approaches c of the constant b will equal that constant b. If you think about it graphically, remember how a limit is where a function is going. So take a look at a function such as this constant function. We'll call it y equals 3. No matter where we are on the function, we are always going to be approaching the y value 3. So for example, if we were to write the limit as x approaches 5 of the constant function 3, we will get the constant number 3. It's all about where the function is going. So we want to think about, perhaps sometimes, what the graph looks like. Other useful properties. The limit of a constant times a function, such as the limit as x approaches c of the constant b times the function f of x equals the constant b times the limit of that function. We're going to explore what these look like more in examples that are coming up soon. The limit of a sum or difference is where we can take the limit of a sum or difference and equate it to the limit of one function plus or minus the limit of the other function. Or in this case, because we defined those limits as L and K, L plus or minus K. We've got the limit of a product, where basically we're doing the same thing as what we do with sums and difference. If we're multiplying two functions, we just take the limit of each function separately and then multiply their limits together. The limit of a power, which is basically the limit of a product. If we're taking the limit of a function raised to a power, we can simply take the limit of that function and raise it to that power. Similarly, the limit of a root, the limit of the root of the function equals the root of the limit of that function. Now, the next one is used quite a bit. The limit of a polynomial function. I like to call that direct substitution, where we directly substitute that value that x is headed towards into that polynomial function. We always try direct substitution first. Let's make that very important note right here. We always try substitution first. It's easy to plug and chug, so why not go with the easiest method, and if it works, we go with it. We have final property, the limit of a quotient. So similarly to the limit of a product, where when we're multiplying the two functions, we can split up their limits, we can also do that with the limit of a quotient. The limit of the functions divided f of x by g of x is equivalent to dividing the limit of f of x by the limit of g of x, as long as the denominator is not equal to 0, and that is an important piece to highlight. If the denominator equals 0, we cannot use this property. So again, we want to make sure we note this is only okay for when that denominator is not equal to 0. Let's take a look at some examples. Use the following information to find each limit. The limit as x approaches 2 of f of x equals 4. The limit as x approaches 2 of g of x equals 5. And the limit as x approaches 2 of h of x equals 6. Notice that all of these have the limit as x approaches 2, as well as these problems, because if x is approaching something else, we will not be able to use this information. That value must match. Let's take a look at this first part. We can rewrite using our properties, such as that constant multiple, where instead this is 3 times the limit as x approaches 2 of the difference of f of x and g of x. And then we can also use that sum and difference property. So we have still the constant multiple, but it's multiplied to the difference between the limits. The limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x. And then we substitute the values that were given above. The limit as x approaches 2 of f of x, that's this part right here, is 4. The limit as x approaches 2 of g of x is 5. So we replace this one, or substitute that, with 5, and then we can evaluate what's remaining. So we have 3 times the difference, 4 minus 5, 3 times negative 1, which makes negative 3. If I keep my work neat, I do not have to circle my answer, which I prefer not to do. Let's take a look at this next one. Now this is a quotient, the limit as x approaches 2 of 2 times f of x plus 1 divided by g of x, the function raised to the third power. Let's use our properties to break this up properly. We'll rewrite this as the limit as x approaches 2 of the numerator, 2 f of x plus 1 divided by the limit as x approaches 2 of the denominator, g of x function cubed, making sure we keep those parentheses that shows that we are cubing the function. Now remember, we can only use that quotient property if the denominator will not equal 0. So let's start by looking or focusing on that denominator. So in the denominator, we can rewrite that as the limit as x approaches 2 of g of x, and that limit will be cubed. Well, if we substitute this part right here with that value from above, this part is 5. And we see that our denominator will not equal 0. So we are safe to continue using this quotient property. Let's now break up the numerator using our properties. So our numerator, 2 times f of x plus 1. The 2 is only multiplied to the f of x, so we will rewrite this as 2 times the limit as x approaches 2 of f of x plus the limit as x approaches 2 of the constant function 1. Notice because 2 is only multiplied to f of x and 2 is not multiplied to 1, the 2 is only multiplied to the limit of f of x, the 2 is not multiplied to the limit of 1. Now let's substitute the information from above for the limit of f of x. That part is 4, And of course, the limit of the constant 1 is just 1. So we can rewrite 2 times 4 plus 1 divided by 5 to the third power. That is an answer, but we can make it prettier. 2 times 4 is 8, plus 1 is 9, so this equals 9 in the numerator over 5 cubed, 125. Finally, taking a look at what happens when we have a root, it works very similarly to how it worked when we had a power. Where we took the power of the limit, we can also take the root of the limit. So this can be rewritten as the square root of the limit as x approaches 2 of the product f of x times h of x. Now, of course, using our product property, the limit of a product, we can also rewrite this as the square root of the limit as x approaches 2 of f of x times the limit as x approaches 2 of h of x. And then we can do our substitution. This limit right here is 4, and the limit of h of x as x approaches 2 is 6. So this becomes the square root of 4 times 6, which is a valid answer, but we can clean that up to be the square root of 24. And better yet, if we would like to simplify this, find our perfect square, which is 4, we can rewrite this as 2 square root of 6. Both of these are valid answers.